Let me welcome you to this lecture. We have been looking at how one can use symmetry considerations to solve different problems related to chemistry, and we have already learned that the wave functions of a molecule, whether in ground state or in excited state, has to form basis for one of the irreducible representation of the point group to which this molecule belongs to essentially. And we have from here we have also learned how one can find out the symmetry selection rules for different transitions, whether it is electronic transitions or it is for vibrational uh, transitions. Now, not only the wave function of molecules form basis for irreducible representation or has to conform to symmetry restrictions, but also a reacting system, that is when a molecule reacts with another molecule, the reacting system or the wave function of the reacting system also has to conform to symmetry restrictions, or the wave function of the reacting system also has to form basis for an irreducible representation in the point group where for which the of the reacting system itself. Now, uh, as such, from here or as such, doing such symmetry considerations or performing such symmetry analysis of a reacting system is quite difficult. But in some of the cases or some of the simple um, reactions, it is possible to do symmetry analysis, and one of these example or one of these concept was put forward by uh, Woodward and Hoffmann, that is R.B. Woodward and R. Hoffmann. So they gave or they put forward some symmetry selection rules for reactions, and these rules are essentially known as Woodward-Hoffmann rules, and these rules, the Woodward-Hoffmann rules, are applicable for only certain systems, only when certain conditions are fulfilled. These conditions are that the reaction must proceed through a concerted process. That is the number one condition that must be fulfilled, that that is what do we mean by concerted process is that the reaction or the reacting system comes reacting molecules come close to each other in a continuous and progressive manner, and then form the product without formation of any intermediate or without involvement of any catalyst or any other non-reacting molecule. So such a process we call the concerted process. And the second important criteria that must be fulfilled for applying these Woodward-Hoffmann rules or selection rules for reactions is that the one or more symmetry elements So one or more symmetry elements must persist during this concerted process of the reaction, and of course this particular the second point is not it does not have to be necessary rigorously followed, because if the symmetry of the reacting skeleton itself is preserved during the reaction, then that itself is enough to use this Woodward-Hoffmann rule, and it does not have to be necessarily uh, uh, fulfilled by the entire molecule. So, for example, give uh, two molecules. Now we see that the symmetry of these molecules are essentially, if we take the overall symmetry of the molecule, then they are going to be different. But when we look at the symmetry of the reacting skeleton, that is the diene group here, that does not change for in case of both of these two molecules, and then we can say that both of these two molecules essentially belong to the same symmetry. They have same symmetry operation, and we don't have to necessarily look at the symmetry by considering the substituents, as long as the electronic nature of the substituents are same. So one has to use their own judgment while finding out whether symmetry or some symmetry elements are being persisting during the concerted process of the reaction or not, and one can ignore the symmetry by considering the substituents if only the electronic nature of the substituents are similar. So if because the methyl group is electronically similar to the ethyl group, so that is why we can ignore the replacement of the methyl group by an ethyl group here. But if we do so by using a carboxylic acid substituent, say for example, or a fluoride substituent over here, then of course they are electronically going to be different, and that is why we can no longer consider them to be of same symmetry. So these two conditions must be fulfilled for using the Woodward-Hoffmann rule. Now these Woodward-Hoffmann rules can be used in many reactions as such, but we will learn these Woodward-Hoffmann reactions by using one very important class of reactions, organic reactions essentially, that is the cyclization of open chain olefins, and these are called also the pericyclic reactions. So we'll learn how the Woodward-Hoffmann rule, or how we can arrive at the Woodward-Hoffmann rule for these pericyclic reactions. Now, of course, before we do that, I would also like to request you to read a paper by Woodward and Hoffmann, where they have accounted for, it's a kind of account paper where they have described this, the basis for this Woodward-Hoffmann rule, and that will allow you to understand this topic in more depth. The paper, or the reference of this paper is, this paper has appeared in Enguante Chemie, and a prestigious international journal, that is NU Chem International Edition in English. The year is 1969. Volume number is 8 and page number is 781. And the title of this paper is The Conservation of Orbital Symmetry. So one should go through this paper to learn the Woodward-Hoffmann rule, or the origin of Woodward-Hoffmann rule in more depth. So we'll now discuss the Woodward-Hoffmann rule, or we will do symmetry analysis of a pericyclic reaction, and we will first discuss the reaction, that is the dimerization of olefin. So as such, the reaction is very simple. You take 2 ethylene and the cyclization reaction occurs to give us cyclobutane. So this is the reaction. Now the reaction happens in a concerted manner here, because the 2 ethylene molecules will come close to each other, and then it will eventually lead to formation of cyclobutane. Then what we see is that when the 2 ethylenes come close to each other, we can find out that the point group of this reacting system is going to be D2H, and the point group of the product here, that is the cyclobutane, is D4H. So now, because D2H itself is a subgroup of D4H here, so that what it means here is that all the symmetry operations of the D2H point group essentially persist during this reaction, that is, during formation of cyclobutane by cyclization of the olefins, and that is why all the symmetry operations of D2H are essentially part of the symmetry operations of D4H point group. So the second condition is also fulfilled. Now, in order to do symmetry analysis, we will have to do some more simplification. That is, when we look at the D2H point group or symmetry operations of D2H point group, we see that there are 8 symmetry operations in the D2H point group. Now, all of these symmetry operations can essentially be generated by considering only 3 planes of symmetry. That is, all these planes of symmetry are perpendicular to each other. So when we multiply these planes of symmetry, any 2 planes of symmetry, then we generate a C2 axis passing through the point of intersection of these 2 planes of symmetry, and that is how essentially we can obtain all the symmetry operations in D2H point group by considering only 3 perpendicular planes of symmetry in this case. So now again, if we look at the molecule, how cyclobutane is essentially formed from the cyclization of 2 olefins, the orbitals that are involved during this process are the pi orbitals, that is pi molecular orbitals of the olefins, essentially interact with each other here, and that leads to formation of the cyclobutane. Now, if you see that one of these plane of symmetry in the D2H point group, that is the plane containing all the 4 carbon atoms in this cyclobutane molecule, or here in case of these 2 reacting ethylene groups, that plane contains all the orbitals that are involved in formation of, or involved in during this process of conversion of ethylene to cyclobutane, because these p orbitals which form the pi cloud on the ethylene group, as well as the sigma orbitals which form the cyclobutane molecules, or sigma bonds that are formed during formation of the cyclobutane molecule from ethylene, they all lie on this plane which contain all the 4 carbon atoms of the cyclobutane, or the carbon atoms of the 2 reacting ethylene groups. So that is why the symmetry of these orbitals, all the interacting orbitals, are not going to change, or all these orbitals which are involved during formation of cyclobutane from ethylene are symmetric with respect to this particular plane of symmetry, and that is why we can only consider 2 planes of symmetry while considering while doing the symmetry analysis of this particular reaction. That is, one of the plane of symmetry is this one over here, and the other plane of symmetry is this plane of symmetry. So here we can rewrite this. This is one plane of symmetry, and that is another plane of symmetry. Let's label this plane of symmetry as sigma b xz, and let's label this particular plane of symmetry as sigma b yz, and the C2 axis of symmetry, of course, now passes through this point of intersection of this particular of these 2 planes of symmetry, sigma b xz and sigma b yz. So what follows from here is that we can do symmetry analysis, or we can only if we consider these 2 planes of symmetry while doing the symmetry analysis of this reaction, that is enough. And from these 2 planes of symmetry, we get another C2 axis of symmetry. So if we consider only the symmetry operations of the C2B point group instead of D2H point group during symmetry analysis of this reaction, then we will be able to essentially find out the selection rules or the Woodward-Hoffmann rules for this particular reaction. So we will consider the symmetry of the orbitals, interacting orbitals with respect to the symmetry operations of the C2B point group here, and then we can proceed further. So in order to do this, let us draw all the orbitals which are involved or which are interacting, and the orbitals that are essentially formed during this reaction, and then look at the symmetry of these orbitals with respect to the symmetry operations of the C2B point group. So we know that the ethylene molecules, they have the pi cloud essentially, we have two pi molecular orbitals in ethylene molecule. One is pi bonding molecular orbital and the other one is pi anti-bonding molecular orbital. Now these orbitals can interact with the orbitals of the another ethylene molecule, and that will essentially lead to the formation of the cyclobutane molecule. And let us find out the different combination of these p-pi orbitals in ethylene molecule that we are going to get over here. So we can have different combinations. We can have combination where two bonding orbitals of the ethylene molecule are now pointed to each other in such a way that the lobes of the ethylene molecules are essentially both are in the same phase. Let us write plus and minus instead of dashed lobes. That will give us a more clean picture over here. So we can have this kind of two bonding molecular orbitals come close to each other, and then that will give us essentially this sort of an interaction over here. Then we can also have two bonding molecular orbitals, but now the lobes are essentially not in phase. Lobes of the molecular orbitals of the two ethylene groups molecules are essentially not in same phase here, but both of them are bonding molecular orbitals, p-pi bonding molecular orbitals of ethylene molecule. But when we when they interact with another ethylene molecule, the lobes are not in the same phase. Then we have pi anti-bonding molecular orbital of ethylene, and the lobes are now interacting. Our lobes of the two ethylene molecules are both in the same phase. Then we have again pi anti-bonding molecular orbital, and the lobes are out of phase with lobes of the two ethylene molecules are essentially out of phase with each other. So these are the combination of different molecular orbitals. These are the four different combinations that we can obtain. Now, if we see if we try to figure out the symmetry of these combinations of p-pi molecular orbitals of the ethylene molecules over here, and that is, let us look at the symmetry of these molecular orbitals with respect to the symmetry operations of the C2B point group. So if we look at these particular molecular orbital over here, we see that with respect to the C2 axis, which is perpendicular to the plane of the board and passes through the center of these two ethylene molecules over here, this combination is symmetric with respect to the C2 axis. So that is symmetric. So this is going to have a symmetry, or it will form basis for an irreducible representation, uh, which is which we can write Mulliken symbol A, or the wave function of this particular reacting system over here, we can denote it as psi A. Then with respect to the xz, sigma v xz, what we see again, sigma v xz is here, xz plane, and yz is over here. So with respect to sigma v xz, it is symmetric in nature. So that is why we can write this is sigma psi as this wave function of this interacting system over here as psi a1. So then next one we can similarly we can write that this is going to be, this can be labeled as psi, because this is not symmetric with respect to C2, so it is psi b, and then with respect to sigma b xz, it is antisymmetric, so that is why it is psi b2, and then this one also we can write, this is again psi b, and with respect to sigma b xz, it is symmetric, so it is psi b1, and for this one we can write it has to be, because this is symmetric with respect to the C2 axis, and it is antisymmetric with respect to sigma b xz, so it is psi a2. Now let us also draw the sigma orbitals that are going to be formed when the p pi orbitals of the two ethylenes are going to interact. So there are going to be again 4 sigma molecular orbitals that are going to be formed from the combination of these p pi molecular orbitals over here, and then we can draw these sigma orbitals of the cyclobutane. So this is plus, 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 minus, minus, minus. So all the lobes here are in the phase. So that is sigma bonding molecular orbital. Then we have another sigma bonding, but this is anti-bonding with respect to the this is there are 2 nodes in this particular molecular orbital, positive positive over here, positive negative, this is positive negative negative, and so these orbitals are in phase, but the sigma interactions over here, they are out of phase. Then we have where only there are 4 nodes total here, one over here, one over here, one over here, and another one over here. So this particular sigma molecular orbital is completely anti-bonding. So this is bonding molecular orbital, you see, and this is slightly bonding, and this is slightly anti-bonding, we can say, and this is anti-bonding molecular orbital. Now we can again find out the symmetry of these molecular orbitals with respect to the symmetry operations of C2P point group, and if we do so here, what we will find in this case, this is psi A1, the wave function is going to be of A1 symmetry here, then this is going to be psi, because it is antisymmetric with respect to the C2 axis, so it is psi B, and then this is B1 because it is symmetric with respect to sigma V xz, and then this is going to be again B, and because it is antisymmetry with respect to sigma V xz, it is psi B2, and this one is psi A2. So now we have the symmetry of the reacting system as well as we have the symmetry of the molecular orbitals in the product. So now let us look at the energy of these different molecular orbitals, or the then we can correlate these molecular orbitals from the reactant, the molecular orbitals of the reactant with the molecular orbitals in the product, and then do a symmetry analysis of this. So when the two ethylene molecules are far away from each other, the two bonding molecular orbitals of the ethylene molecule, that is the p-pi bonding molecular orbitals of the ethylene molecules, are going to be degenerate with each other. So that is, in that case, what we see is that the energy of psi A1 and psi B2, these are going to be essentially degenerate when the two ethylene molecules are far away from each other. Now once and then the two antibonding molecular orbitals, that is the psi B1 and psi A2, are also going to be degenerate with each other when the two ethylene molecules are far away from each other. So this is the energy scale we can write. So the bonding molecular orbitals are of lower energy than the antibonding molecular orbitals. Now when the two ethylene molecules come close to each other, what we see is that this is a bonding situation arises over here, while anti-bonding situation arises in this case, and that is why the energy of psi B2 is going to increase while the energy of psi A1 is going to decrease as the two ethylene molecules come close to each other. And there will be a bifurcation of energy of these two molecular orbitals over here, and similarly the energy of these two antibonding molecular orbitals, psi A2 and psi B1, antibonding with respect to pi bond over here, that is these two molecular orbitals here. What we see is that this leads to bonding, sigma bonding interactions, and this leads to again sigma antibonding interactions, since that is why the energy of psi B1 is going to decrease while energy of psi A2 is going to increase. And now if we look at the energy of the product over here, that is the cyclobutane molecule, and the energy of the energy of these wave functions in case of the product here, what we see is that A1, psi A1 is completely bonding, and that is why it will have lowest energy. Then we have psi B1, which is of course antibonding with respect to pi interaction, but bonding with respect to sigma interaction, since sigma interaction is much more stronger than pi interaction, and that is why there will be overall, this is going to have lower energy over here. So this is psi B1, and then we have the psi B2, and then we have psi A2, because that is completely antibonding in nature, and that is why we have highest energy. So let us now correlate the orbitals or the wave functions of the same symmetry from the reactant with those of the uh, molecular orbitals of same symmetry in case of the product here. So that is psi A1, we see that is the bonding here, and psi B2 is this one, and that is psi B1, and this is psi A2. Now let us also fill the electrons in these in the reacting system as well as in case of the product over here. So we know the bonding molecular orbital or pi bonding molecular orbital in ethylene contains 2 electrons, since we have 2 ethylene molecules. So that is why total 4 electrons, and they will be here in this way in both the bonding molecular orbitals in the reacting system, and that is the case over here as well. But and in case of the product, in case of cyclobutane, the 2 electrons are again going to occupy the 2 bonding molecular orbitals over here. Now we should this picture we can call as the orbital correlation diagram. Now from here what we see is that the symmetry of these molecular orbitals has to persist, or the symmetry of these molecular orbitals with respect to symmetry operations of C2b point group has to persist during the course of the reaction, that is dimerization of ethylene, and that is why these that is how we can correlate these molecular orbitals of the reacting system with those molecular orbitals of same symmetry in case of the product over here. And now what we see is that during formation of cyclobutane starting from ethylene, the one of the bonding molecular orbital in ethylene, actually that is the psi B2, becomes an antibonding molecular orbital in case of the product. So as such, this when the when the cyclobutane molecule is formed, so that means the 2 electrons are going to be present in this particular molecular orbital. So cyclobutane molecule is going to be formed when we do dimerization of ethylene. The cyclobutane molecule is going to be formed in an excited state, and then it has to release energy or radiate energy to come down to the ground state. As such, it would not have been a problem, but in order to obtain the cyclobutane molecule in higher energy state, we need to provide extra energy, and this much of energy, it is difficult to attain this much of energy by, or activation energy by using thermal methods, by heating the ethylene molecules, and that is why this particular reaction, that is the dimerization of ethylene, does not proceed through thermal conditions, or thermally it is forbidden. The reaction is thermally forbidden, and that's what we understand from this particular orbital analysis. So this essentially brings us to the end of this lecture. What we have so far learned during this lecture is that we have learned that one can use symmetry considerations in different reactions as well, provided certain conditions are fulfilled, and the Woodward-Hoffmann rules actually gives us, or put forward a concept where we can use symmetry considerations provided 2 important conditions are fulfilled. That is, number 1 is that the reaction must proceed through a concerted process, that is where the reactants come close to each other in a continuous and progressive way, and the reaction completes without formation of any intermediate or without involvement of any catalyst or any other non-reacting molecules for that matter. Then the second important criteria is that one or more symmetry elements must, or symmetry operations must persist during the entire course of this concerted process, and from here, we have also learned that this does not have to be necessarily followed very rigorously, because if only the reacting skeleton or the symmetry of the reacting skeleton is conserved during the reaction process, and we can ignore the symmetry or symmetry of the molecule by ignoring the substituents on the reacting skeleton atoms, provided again if the electronic nature of these substituents are similar. Then we discussed the Woodward-Hoffmann rules in terms of a very important class of reactions, that is the pericyclic reaction, and the example that we have taken is the dimerization of olefin, and we discussed the dimerization of ethylene to obtain cyclobutane, and then we saw that only if we consider the symmetry operations present in the C2B point group during this reaction process, then we can do complete symmetry analysis of this reaction, and then we obtain the orbitals which are involved in this reaction, that is the p-pi orbitals of the ethylene molecule and the sigma molecular orbitals of the cyclobutane molecules in the product, and then we deduce the symmetry of these or molecular orbitals in terms of the with respect to the symmetry operations of C2B point group, and based on that we could draw something known as the orbital correlation diagram, and this orbital correlation diagram here shows us that one of the bonding molecular orbital in the reacting system has to become an antibonding or becomes an antibonding molecular orbital in the product. And because this molecular orbital is filled molecular orbital, that is the psi B2 molecular orbital is a filled molecular orbital, so during the reaction process, the cyclobutane molecule is formed with 2 electrons in psi B2 and no electrons in psi B1, so it is essentially formed in an excited state. And such a reaction, that is why is difficult to be carried out or forbidden by thermal methods, and this essentially explains that why the dimerization of olefin does not proceed thermally. So we will discuss more about this reaction, that is dimerization of olefin, and we will involve electronic states also into our discussion, or the symmetry of electronic states, not only the symmetry of the interacting orbitals, it's only, and that will allow us to understand more or do more symmetry analysis of this particular reaction. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.